Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. GATE 2022 Chemical Engineering. Previous year questions and solutions. Heat transfer. In this video, we will discuss the following questions with solutions with detailed analysis of the concepts involved. Question number 9, question number 12, question number 16, question number 43, and question number 44. I would appreciate if you subscribe to the channel. It will motivate us to produce more valuable knowledge content for your career progress. So subscribe now before you forget. GATE 2019 Heat Transfer. In the last two videos, we discussed GATE 2019 Chemical Engineering questions in mass transfer. In this video, we will discuss the questions in heat transfer with detailed analysis and solution. Question number 9. Pool boiling equipment above ambient temperature is usually designed to operate option A, far above the critical heat flux, option B, near the critical heat flux, option C, far above the Leidenfrost point, option D, near the Leidenfrost point. Before we go into the solution part, spend a couple of minutes in understanding the concept of pool boiling. What is pool boiling? Boiling is a process that occurs at a solid-fluid interface when a liquid comes into contact with a solid surface that is maintained at temperature sufficiently above the saturation temperature of the liquid. An example of what we do every day at home, heating of water at home in a kettle on a gas stove. Pool boiling is a boiling process that takes place in the absence of bulk flow. Another type of boiling is flow boiling that takes place when the fluid is forced to move through the heated pipe or a surface by a pump. This figure illustrates the pool boiling concept. The liquid in the vessel is in contact with the hot surface of the vessel, which is heated externally. Any motion of the fluid is due to natural convection. The buoyancy causes the bubbles to move up, as shown. This is a plot of delta Txs, which is T surface minus T saturated versus boiling heat flux Q. There are four distinguished zones. As the heating surface temperature increases, the delta Xs increases for a given boiling pressure, and the heat flux increases. Accordingly, four forms of boiling takes place: natural convection boiling, nucleate boiling, transition boiling, and film boiling. In the natural convection boiling, the heat transfer from the heating surface to liquid is by natural convection. In the region A to B, bubbles form at an increasing rate, at increasing number of nucleation sites as we move along the boiling curve to point C. In the AB region, isolated bubbles. In the B to C, numerous continuous columns of vapor. In the AB region, the increased heat transfer is due to agitation formed by the entrainment of liquid to heat a surface, as also large heat fluxes. The maximum heat flux corresponds to the point C. The heat flux at this point is called critical heat flux. After that, with the increase in delta T excess, the heat flux decreases and reaches point D, called Leidenfrost point. The decrease in heat transfer and hence heat flux is due to covering of heating surface by vapor film. In the transition regime, both nucleate and film boiling occur. As the delta T excess is increased further, heat transfer increases due to radiation to the liquid. The heat surface is covered with a stable film. A typical boiling process does not follow the boiling curve beyond the point C. As seen in the boiling curve, the maximum or critical heat flux is usually achieved in boiling that corresponds to point C. For engineering or design purposes, the maximum or critical heat flux is more important. Hence, the answer to the question is option B. Before we move on, I would like to make a call to my dear viewers. Your SPEC e-learn channel is a one-stop learning and skill development channel for your career. So do not forget to subscribe. Please press the subscribe button right now. Question number 12. A thermocouple senses temperature based on option A, Nernst effect, option B, Maxwell effect, option C, SPEC effect, option D, Peltier effect. Thermocouples are temperature sensors which are extensively used for measurement of temperatures in process and non-process industries. Hence, it is important that you understand the working principle. The thermocouple working is based on SPEC effect. According to SPEC effect, when a closed circuit is formed by joining two dissimilar metals at two junctions, and the junctions are maintained at different temperatures, then an electromotive force EMF is induced in the closed circuit. The amount of EMF produced is different for different metal combinations. The EMF produced is proportional to the temperature difference of the junctions. This figure illustrates the setup for thermocouple for temperature measurement. The EMF is of the order of millivolts. It can be measured by an electrical instrument as shown in this figure. The meter can be calibrated in terms of temperatures. The thermocouple can be used to measure temperatures up to 1400 degrees centigrade. Different metals are used for different temperature ranges. Thermocouple responds to temperature changes very quickly. The answer for this question is option C. Consider the two countercurrent heat exchanger designs for heating a cold stream from temperature T1 to T out as shown in this figure. The hot process stream is available at capital T in. The inlet stream conditions and overall heat transfer coefficients are identical in both the designs. The heat transfer area in design 1 and design 2 are respectively A1HX and A2HX. The two heat exchange designs for the questions are given below. If the heat losses are neglected And if both the designs are feasible, which of the following statements hold true? Option A, A1HX greater than A2HX and T1 out less than T2 out. Option B, A1HX equal to A2HX and T1 out equal to T2 out. Option C, A1HX less than A2HX, T1 out greater than T2 out. Option D, A1HX less than A2HX, T1 out equal to T2 out. Study the two heat exchanger design closely and you will notice a difference. In the design 2 heat exchanger, some of the cold stream is bypassing the heat exchanger and joining the exit stream. Given that the overall heat transfer coefficient is the same in both the design, the energy balance equation for any heat exchanger is written as F in CPC times small t out minus small t in equal to F in CPH into capital T in minus capital T out. The quantity of heat exchanger is reduced in the design 2 due to bypassing. Hence, the hot fluid outlet temperature will be reduced to the extent of reduction in heat duty. However, if you provide a larger area, then the outlet temperature of the cold fluid in the design 2 heat exchanger will increase and the heat transfer also will increase. At some value of area A2HX for the design 2, T2 out will become equal to T1 out. Since it is given that the inlet stream conditions are the same in design 1 and design 2, we have the following. Small f in design 1 equal to small f in design 2. Capital F in design 1 equal to capital F in design 2. Capital T in and small t in design 1 equal to capital T in and small t in design 2 respectively. CPC and CPC hot in design 1 is equal to CPC and CPC hot in design 2 respectively. Heat transfer based on the hot fluid in design 1 is Q1 equal to F in times CPH times T1 in minus T1 out. Likewise, heat transfer based on hot fluid design 2 is Q2 equal to F in times CPH times T2 in minus T2 out. We have the area of the design 2 A2HX such that T2 out equal to T1 out. For this situation, the heat exchanger design 1 and design 2 will be equal. Now you write the equation for heat transfer Q in terms of the overall heat transfer coefficient. Q is equal to U times A times log mean temperature difference. For the design 1 and design 2, we can write U1HX into A1HX the delta T1 ln Hx equal to U2HX times A2HX times delta T2 ln Hx. Before we move on, I would like to make a call to my dear viewers. Your SPEC e-learn channel is a one-stop learning and skill development channel for your career. So do not forget to subscribe. Please press the subscribe button right now. Since it is given that U1HX equal to U2HX, the above heat transfer equation simplifies to A1HX delta T1 ln hx equal to A2 hx times delta T2 ln hx. For the design 1 heat exchanger and design 2 heat exchanger, we have capital T in 1 equal to capital T2 in, capital T1 out equal to capital T2 out, and small t1 in equal to small t2 in. Only the outlet temperatures are different. That is, T1 out is not equal to T2 out. It is apparent that the flow of cold fluid in design 2 heat exchanger is less than that through the design 1 heat exchanger due to the bypassing effect. Hence, we have the situation where T2 out is greater than T1 out. Hence, delta T1 ln Hx is greater than delta T2 ln Hx. That leads us to the conclusion that A2 Hx is greater than A1 Hx. Hence, for the two designs of heat exchangers, A1 Hx is less than A2 Hx and T1 out equal to T2 out. So the answer for the question is option D. Question number 43. Stream A with specific heat capacity CPA equal to 2000 joules per kg degree Kelvin is cooled from 90 degrees centigrade to 45 degrees centigrade in a concentric double pipe countercurrent heat exchanger having a heat transfer area of 8 square meter. The cold stream B with heat capacity CPB equal to 1000 joules per kg degree Kelvin enters the exchanger at a flow rate of 0.1 kg per second and 40 degrees centigrade. The overall heat transfer coefficient is U equal to 250 watt per meter squared degree Kelvin. Assume the mean driving force is based on arithmetic temperature difference delta T AMTD, which equals TA in plus TA out by 2 minus TB in plus TB out by 2. The mass flow rate of the stream A in kg per second is the heat exchanger, and the temperature data for the problem is depicted in the figure shown. The hot stream entering at 90 degrees centigrade and is leaving at 45 degrees centigrade. The cold stream enters at 40 degrees centigrade and flows countercurrent to the hot stream. The temperature difference across the heat exchanger is given that delta T AMTD equal to TA in plus TA out by 2 minus TB in plus TB out divided by 2. Also given are overall heat transfer coefficient U equal to 250 watt per meter square degree Kelvin and the area A is equal to 8 square meter. So the heat exchanged in the exchanger is Q equal to UA delta T AMTD, which is equal to 250 times 8 times delta T AMTD, which comes to 2000 delta T AMTD joules per second. The heat exchanged by the cold stream is Q equal to MB CPB times TB out minus TB in. Substituting the values, we get Q is equal to 1 times 1000 times TB out minus 313 joules per second. Equating the two equations for heat transfer, we get 2000 times 90 plus 45 divided by 2 minus 40 plus TB out by 2 equals 1 times 1000 times TB out minus 313. Solving the equation by iteration, we get TB out equal to 243 degree Kelvin, which equals 70 degrees centigrade. Substituting the values of TB out in the equation for the heat exchanged by the cold fluid, we get Q is equal to 1 times 1000 times 343 minus 313, which works out to 30,000 joules per second. Heat exchanged by the hot fluid stream A equals K equal to MEA times CPA times TA in minus TA out, which is equals 30,000 joules per second. Substituting the data for hot stream, that is stream A, and solving the above equation, we get the mass of the stream A equal to 0.3 kg per second. Question number 44. A 20 cm diameter cylindrical solid pellet of a nuclear fuel with a density 6000 kg per cubic meter and conductivity 300 watts per meter Kelvin generates heat by nuclear fission at a spatially uniform rate of 10 to the power 4 watts per kg. The heat from the fuel pellet is transferred to the surrounding coolant by convection such that the pellet wall temperature remains constant at 300 degrees centigrade. Neglecting the axial and azimuthal dependence, the maximum temperature in degree centigrade that can be achieved in the pellet at steady state is this figure shows the arrangement of nuclear fuel pellets or rods which are cylindrical in shape in the core of the nuclear reactor. Due to nuclear fission, heat is released. Since the fission energy is generated within the core, which consists of several fuel pellets, the temperature is maximum at the center. The heat flows to the surface by conduction, and the coolant surrounding the fuel core maintains the temperature of fuel pellet surface at TW. With the given data as shown in the figure, you are asked to determine the maximum temperature T max in the fuel pellet under steady state. This is a transient heat transfer problem in a cylindrical solid body. The heat transferred is a function of the time and distance. Since the temperature of the body receiving the heat varies with time and distance, hence T is a function of R and T. In this problem, only radial conduction is considered. Axial conduction is ignored. Hence, the problem is limited to one directional radial conduction. Radial conduction in a cylindrical fuel is given by the equation rho C into Cpc into dou T of by dou T equal to Kf times 1 by R dou R of R times dou Tf by dou R plus Q triple dash, where rho C is the density of the fuel element, Cpc is the heat capacity of the fuel element, Tf is the temperature of the fuel element, Kf is the thermal conductivity of the fuel, T is the time, R is the radius of the fuel pellet. Q triple dash is the heat generated in the core per unit pellet volume. At steady state, dou Tf by dou T is equal to 0. Hence, the above expression becomes 1 by R d by dr of R times dTf by dr equals minus Q triple dash by Kf. Rearranging, we get d by dr of R times dTf by dr equals minus R times Q triple dash divided by Kf. Rearranging and integrating with the application of boundary conditions, we get the expression for temperature difference within the fuel pellet. Tmax minus Tw equal to R squared Q triple dash divided by 4 times Kf. This is the expression we will use for solving this problem. Note down and memorize this formula for quick recall. Given are the following data. Diameter of the cylindrical pellet df is 20 cm. Density of the pellet ρf is 6000 kg per cubic meter. Thermal conductivity of the pellet Kf is equal to 300 watts per meter K. Heat generated by nuclear fission is 10 to the power 4 watts per kg. The characteristic length for the pellet Lc is determined from the following formula. Lc equals pi r squared L divided by 2 pi r times L plus R. If L is very much greater than R, then Lc becomes R by 2. So Lc becomes 0.1 by 2 equal to 0.05 meter. The volume of a solid pellet Vf is equal to pi r squared Lc. This is equal to 0.00157 cubic meter. Surface area of the pellet is obtained from this formula. AF equal to 2 pi r Lc, which works out to 0.0314 square meter. The mass of the fuel pellet M is equal to rho F times Vf, which works out to 9.429 kg. The heat generated by fission equals 10 to the power 4 watts per kg, which works out to 94290 watts. The heat generated per unit volume of the fuel pellet is obtained from Q triple dash equal to 94290 divided by Vf, which works out to 60 into 10 to the power 6 watts per square cubic meter. The maximum temperature of the fuel pellet at steady state is obtained from the expression which is previously given. Tmax minus Tw equal to R squared times Q triple dash divided by 4 Kf. On substituting, we get Tmax minus Tw equals 500 degree Kelvin. The maximum temperature of the fuel pellet at steady state becomes Tmax equal to 500 plus 573, which works out to 800 degrees centigrade. So the answer to the question is 800 degrees centigrade. Please subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With this, we have come to the end of the presentation. Please give your comments, if any, about this course after you finished viewing this video. Share with your friends and colleagues to reach out to large number of career-oriented professional students. Thank you for watching.